I am so glad you convinced me that the family car should be the Defender 110. It is so beautiful inside, it's so comfortable, and it just feels indestructible.
Yes, it really is. I've been waiting a long time for the new model to come out. The Defender 110, I'm telling you, it's my favorite car of all times. It's my third one. You know, I have stories of going off-road. The guy managed the group. He was like, what are you doing in this beautiful car? I'm like, I'm going off-road. He's like, are you sure? Because you can use one of ours. And then they look like Mad Max cars. I'm like, no, we're going to do this. And he was shocked.
Wow. Well, it's great because the Defender has been reimagined for 21st century adventure, and its unparalleled off-road ability, as well as its robust interior, are invaluable whether you're headed towards uncharted territory or just a weekend of exploration. The Defender 110 tackles challenging surroundings with absolute confidence. The SUV conveys strength outside and in, featuring peerless technology like an intuitive driver display and an award-winning infotainment system. That's my favorite part, to keep you connected no matter where the journey takes you. Adventure is unique to everyone, and so is the Defender. Choose from the two-door Defender 90, the four-door Defender 110, or the larger Defender 130 with the ability to seat up to 8 passengers. You'll find uncompromising performance in all three. So pack up and go even further with the Defender 110. Learn more at LandRoverUSA.com/Defender.
These days, we're all investors, trying to be smart with our money despite our worst impulses. But at iShares, we believe that deep down inside of every investor is a better investor. One that's just waiting to be let out. Explore iShares ETFs and insights and let your best investor out. Visit iShares.com for more information.
This isn't your average business podcast, and he's not your average host. This is the James Altucher Show. Today on the James Altucher Show.
What if you get paid to ask questions about, is time travel possible? Is teleportation possible? What happened before the universe began? What is the smallest possible thing that an atom or a quark could be divided into? What's in the center of a black hole? Oh, all these things. You get the idea. Well, Michio Kaku, not only is he a great physicist and a great writer, and we're here to talk about his new book, The God Equation, The Quest for a Theory of Everything, but he's also just generally enthusiastic about life and about what he does. To me, he's like a modern day philosopher, and I love just talking to him and hearing his imagination at work. So there's some physics stuff in here, but then I ask, how can we build a time machine? And he gets into it. Here he is. Thank you for joining the podcast once again.
Mm-hmm.
I really enjoyed The God Equation.
Oh, okay.
And I'm not just saying that. I feel like I learned new things about physics.
Mm-hmm. Right.
Often I read things, and I learn things at a very basic level. Like when you start explaining what gravity is in different theories of gravity in the first couple of chapters.
Mm-hmm.
And then I started to understand. Anyway, you're one of the founders or developers of string theory and string field theory.
Mm-hmm.
And I wanted to ask you so many questions, but first, why did you call it the God Equation?
Well, first of all, the use of the word God starts even before Einstein began to be interested in it. But Einstein wrote extensively about, quote, the mind of God. And Stephen Hawking then also talked about the mind of God. And in mathematics, there's also a God equation. Leonard Euler in the 1800s wrote a simple equation with the number 1, 0, pi, e inside. One equation that summarized the basic constants of mathematics. One equation. Well, a God equation for physics would be even more powerful, uniting not just 1, 0, pi, and e, but uniting the fundamental forces of the universe. And so in the same way that the God equation of mathematics unifies the constants of mathematics, the God equation of physics unifies the forces that govern the universe. the gravitational force, the electromagnetic force, and the two nuclear forces into one equation. And that equation in turn set into motion Genesis. So the Bible, of course, talks about God setting it into motion. But if you believe in God, then how did God do it? Well, he had to have an architecture. And this is the God equation. The God equation basically allowed God, or whatever, to set the universe into motion, giving instructions for how to combine particles to create atoms and nuclei and people as well. And so that's why the word God equation is actually rather common in physics. In fact, there's even a God particle in physics. A Nobel Prize winner, Leon Lederman, called the God particle a particle that in some sense helped to set off the bang of the Big Bang. The original universe had a symmetry associated with it, but we don't see that symmetry here today. It's all broken. There's no one symmetry. There's no superforce anymore. We have lots of smaller forces. So the original symmetry of the Big Bang broke. But what broke the symmetry? This is where the Higgs boson comes in, the God particle. The God particle, in some sense, helped to break the original symmetry, shattering it to give us eventually the Big Bang. But what's the equation that governed the particle? That's the God equation.
And, and by the way, we're going to get to time travel and teleportation in a little bit, which is obviously subjects of great importance to everyone. But, obviously, there was a problem in unifying Einstein's theories of relativity and Newtonian physics with what was being discovered in quantum mechanics. It didn't make sense to Einstein, and the people who developed quantum mechanics also didn't have a solution to kind of unify all these theories. You have been working for 40 years almost on string theory, which sort of postulates, and correct me if I'm wrong, I'm just trying to understand these concepts, postulates that every atom and quark and electron and proton and energy and force, whatever, can all boil down to strings vibrating at different frequencies. Very tiny, tinier than a quark strings that are vibrating at different frequencies.
Right. You see, all of biology can be explained in terms of chemistry. All of chemistry, in turn, can be explained in terms of physics. All of physics, in turn, can be explained in terms of two theories: the quantum theory, the theory of the very small, and general relativity, the theory of the very big. The problem is these two theories hate each other. They're incompatible. They're based on different mathematics.
What exactly is the incompatibility?
Well, first of all, let's take a look at general relativity. General relativity is based on smooth surfaces like trampoline nets, smooth surface like bed sheets. And we are actors and actresses dancing on this smooth surface, which gives us gravity. Gravity is caused by the smooth bending of space. Now, the quantum theory, the theory of transistors, atoms, lasers, the internet, this conversation is made possible because of the quantum theory. The quantum theory is the exact opposite. It takes things and chops them up into tiny little particles. So we have two opposites, one based on smooth surfaces and the other one based on chopped up particles. Now, Einstein said this is like his theory of gravity being made out of marble. He thought that gravity was like marble, smooth, beautiful, gorgeous, but matter in the quantum theory, wood, gnarled, all sorts of roots and branches and all sorts of hideous things coming out. And so Einstein wanted to make a theory of pure marble. He wanted to turn wood into marble. That was his goal. Unfortunately, he failed. So now we have a new theory. And the paradigm that unifies matter and relativity, we think, is music. Music is rich enough to summarize the vast varieties of forms we see in the universe. Now, how's that possible? Well, take an electron. If I have a super microscope and could peer into an electron, normally you would think that it's a dot particle. Nope. String theory says that it's a rubber band. A rubber band. And if you twang it, it vibrates at a different frequency. So we have to give it a different name. We call it a neutrino. We twang it again, and it turns into a quark. We twang it again, it turns into a lepton. And if you twang it enough times, it turns into all the subatomic particles, this zoo of subatomic particles that we have found since World War II. And so physics becomes the harmonies that you can write on these vibrating strings. Chemistry is the melodies you can play on these vibrating strings. The universe is a symphony of these strings. And then the mind of God that Einstein spent 30 years of his life chasing after, the mind of God would be cosmic music resonating through hyperspace. That would be the mind of God.
Now, I'm wondering, like, obviously it's a theory, it's called string theory, but is it more, and maybe there's no difference between this, but is it more of a model? Is it more of a metaphor that somehow mathematically then unifies these theories? Like, are there really strings that are vibrating at different frequencies? Or is this just a way to kind of break down in even smaller units so that everything could then populate it higher and explain everything?
Well, strings are not a metaphor. They actually are vibrating strings, not ordinary strings, but these are what everything else is made of. People ask, what is a string made of? Well, strings is the building block from which you can build everything else. So the closest you can get is that strings are pure energy. The pure condensation of energy would be these strings, out of which you create electrons and neutrinos as nothing but different notes on this tiny vibrating string. And so we have a unified theory then of forces and particles. Now, if Einstein had never been born, we would have discovered relativity anyway as nothing but the lowest octave of the vibrating string. Now, I find this absolutely stunning. The fact that the lowest vibrations of this string contain all of Einstein's theory of general relativity, including the standard model.
Now, what does that mean? Like, how do we know that? Like, what does that mean, really?
That means if I have the equations of a vibrating string, and I work out the properties of these vibrating strings, we find that one of these particles has spin 2. Particles have spin. Spin 2 particles are gravitons, particles of gravity that are chopped up. And then when you put them into the equations, you get all of Einstein's theory coming out. So all of general relativity, the sum total of all the beautiful mathematics of relativity, come naturally as nothing but some of the lowest notes on a vibrating string. I find that absolutely stunning, absolutely incredible, that if Einstein had never been born, we would have discovered string theory anyway as a byproduct.
And I mean, again, like, how do you know, yes, it's a bunch of equations, it's many mathematical equations and decades of work, but how do you really know that this is the unifying theory? Like, right now, every schoolboy grows up learning about the atom, the electron, protons. These are observable. And then, okay, I think relativity is a concept a little harder to understand, but we understand that because of his theory of relativity, the speed of light is the maximum speed you could travel, and everything else, space, time, whatever, gravity is relative to that. And what does it mean to have a unified theory? Like, what wasn't being unified before? I'm not sure I understand that part.
Well, the particles that we see in nature generate forces, and there are 4 fundamental forces that rule the world. Gravity, which keeps us on the floor, the electromagnetic force, which lights up the cities, and the 2 nuclear forces, which light up the stars. That's why the sun shines. That's why we have nuclear weapons. That's why we have nuclear power plants. So we have 4 fundamental forces. 3 of them can now be combined into the quantum theory. But the other theory, general relativity, is the bad boy. They don't combine. They're based on different mathematics, different principles, different everything. They simply do not want to combine until you go to string theory. And then you ask for some proof of string theory. First of all, the simplest proof of string theory is to show that the standard model of subatomic particles, which seems to describe neutrons and protons and things like that, that it is missing something. It is missing a fifth force beyond gravity, electromagnetism, and the 2 nuclear forces. And just 3 weeks ago, we might have found the signal that there is a fifth force. Outside Chicago, at Fermi Laboratory, they found that the muon, a subatomic particle, does not obey the usual equations of the Standard Model. For 50 years, we've had the Standard Model. It's an ugly theory, not elegant at all. It's a theory that only a mother could love, but it works. It describes the low energy behavior of subatomic particles out to 14 trillion electron volts. But beyond that, maybe it breaks down. And maybe string theory comes in as a fifth force and a sixth force. And just 3 weeks ago, we found evidence that that could possibly be correct. We may be witnessing the birth of a new force in nature that is predicted by string theory. String theory predicts something called dark matter. Dark matter is invisible matter. It holds the galaxy together. It's one of the big mysteries of cosmology. Why is the universe mainly made of something called dark matter and not atoms? Dark matter could be just another particle in the musicology of strings. So string theory makes several predictions. It predicts it should be a fifth force. It predicts it should be dark matter. And it even predicts things like the possibility of wormholes, time travel, but we'll talk about that in a moment.
Yeah. So with all the other forces, the nuclear forces and electromagnetism, these play a valuable role in how the universe functions. We can understand it. Like you say, the nuclear forces light the stars, the electromagnetism lights the cities. Gravity, we know what gravity does. It keeps us to the ground. What do you think the fifth force or sixth force or whatever, what would these other forces be doing?
Well, dark matter, we think, could be one of the fifth, sixth forces that we're talking about beyond the Standard Model subatomic particles. And what does it do? It holds the galaxy together. If it wasn't for dark matter, the Earth would have been flung into outer space billions of years ago. We wouldn't be here. We wouldn't be here to talk about it. And so it holds the galaxy together, dark matter.
So dark matter might have enough sufficient mass that it keeps the universe from flinging out completely, and completely dissipating. It kind of holds things together via its own force, which is like gravity.
Well, it holds the galaxy together, not the universe, but the galaxy. So we have galaxies in outer space, but they spin too fast. They spin 10 times too fast. According to Newton's laws of motion, they should fly apart, but they don't. Galaxies are stable for billions of years. So there's another force, a new force that holds the Milky Way galaxy together, a halo that surrounds the Milky Way galaxy, and it's invisible because, of course, we don't see it. That's why we missed it for so many years, thinking that what we saw in a photograph was all there is, not realizing that there was an invisible matter holding the galaxy together. That's why we're here today to talk about it. And string theory predicts a particle called the photino, which could be dark matter because it is invisible, it has mass, and has gravity, all the ingredients you need to create dark matter. And dark matter, in turn, makes life possible. In fact, we live in a wind of dark matter. As the Earth moves around the sun, it's traveling in a wind of dark matter, but we don't feel it because it has no electromagnetic properties. But we could be actually moving in a wind of dark matter right now, even as we speak.
Now, wouldn't string theory predict any particle? Like if I said there's a new particle created by black holes, for instance, can I use string theory to say, okay, it's just another vibration of another string?
That's right. There are an infinite number of vibrations of the string. And there are so many subatomic particles, you get frustrated and angry. How could nature be so vicious to create this zoo of subatomic particles? G. Robert Oppenheimer, the father of the atomic bomb after World War II, was so frustrated that we had so many particles that he said that, quote, the Nobel Prize in Physics should go to the physicist who does not discover a new particle this year. That's how bad it is. How can nature be so malicious to create a zoo of subatomic particles with no rhyme or reason? Well, the answer is, it's music. Nothing but musical notes. That's the simplest paradigm that even children understand. And yes, that explains the diversity of music and the diversity of matter on the Earth.
So this is great because I think for the first time in my life, after trying to understand this, I'm starting to understand. So at the quantum level, the super tiny level, ever since quantum mechanics started, we've noticed that things like light are both, particles like photons, and they're also waves at the same time, which is mysterious and confusing. But perhaps with string theory at this quantum level, when we view them as a vibrating string, it looks more like a wave, and we view them as, but it kind of congeals into particles when we try to observe them. Am I starting to get close?
Well, sort of. But remember that string theory is a quantum theory, okay? It's not Newtonian. It has a wave function, and these wave functions can vibrate, and these vibration modes are particles. And so we have two pictures that are involved with creating strings, just like with ordinary particles, except now we're replacing point particles with vibrating strings.
But is this why what's confusing is something that can explain both the four basic forces and particles? And is this because the forces, when viewed at the quantum level, are both forces and particles, and the string theory can explain why they're observed in both ways?
Well, that's one way to look at it. The dual nature of it is the fact that matter can both have particle characteristics as well as wave-like characteristics. But I should also point out that a vibrating string can also create a wave function associated with it. And that wave function in turn is a field. And the theory of that is summarized by string field theory, which I created. String field theory allows you to summarize the vast number of particles as musical notes in an equation 1.5 inches long. Now, Einstein wanted to get it down to 1 inch. My equation is 1.5 inches long, and it summarizes all of string theory. But it's not the God equation, because it turns out that we now have membranes in addition to strings. And so far, no one has been able to create a field theory of strings and membranes. That has eluded the finest minds on the earth so far. So I tell people that if they're watching this program and they want to win a Nobel Prize, they should create the God equation, the field theory of strings and membranes. And what you do first, you should tell me. Tell me first. And we'll publish together, and we'll win the Nobel Prize together.
If you were to win the Nobel Prize right now, what would it be for?
Well, just remember that Einstein's theory created an equation, general relativity, which in turn spawned many, many other Nobel Prizes, sort of like crumbs off the kitchen table. Even the crumbs off the kitchen table of relativity have given Nobel Prizes to scores of physicists. The Nobel Prize was given to people who discovered gravity waves, predicted by Einstein in 1916, for example. Black holes, predicted by Einstein in 1916. So all these Nobel Prizes are being given to scientists who are working on crumbs off the table of Einstein.
For you, if next year the Nobel Prize in Physics was to be awarded to you, what would it be for? Would it be the development of string field theory?
Well, string field theory is not enough. It's not radical enough. We want an even higher theory, which I'm trying to work on now, because there are membranes in addition to ordinary strings. And so far, some of the brightest minds on the earth are working on this problem. But so far, no one has been able to get a satisfactory theory of strings and membranes. Membranes like a beach ball. A beach ball would be a membrane. A football would be a membrane, as well as a violin string, which represents a string, of course. And so no one has been able to get that final theory. But I think that the person who does get it could be in line for a Nobel Prize.
And why are there so many skeptics to string theory? People like the standard model, and they're willing to accept the fact that they can't be unified. And when I say people, I mean physicists.
Most physicists believe that the standard model is a halfway house. It is so ugly, so contrived, so clumsy, that nature could not have created at the fundamental level a theory that is this disjointed. It's like taking an aardvark, a platypus, and a whale, scotch taping them together and declaring that to be nature's finest evolutionary achievement, the end product of millions of years of evolution on the planet Earth. Nobody thinks that the standard model is the final theory. However, it works. At the low energy realm, it fits the data. It's indisputable. But at high energies, we're looking for cracks. And the first crack may have been found 3 weeks ago at Fermilab, the first major crack in 50 years, indicating a fifth force, indicating a new force out there.
What happened at Fermilab? There was I remember you talking about it in something else. There was like an earthquake or?
It's a figurative earthquake. What happened is that the standard model predicts the magnetic properties of these particles. The electron has partners. One of the partners is a muon, a mu meson. It's one of the constituents of cosmic rays. You have mu mesons going through your body right now. Even as we speak, there are mu mesons.
No, I wear clothes to protect me from that.
Yeah, but anyways, these are cosmic rays. And the standard model predicts their magnetic properties. But when we actually measured the magnetic properties of the muon, it was off. And it shouldn't be that way. People were shocked. What? The first deviation from the standard model? This is big news. And so we now realize there could be a fifth force. A fifth force, and forces are mediated by particles. And these particles are, as I said, we think musical notes on a vibrating string. It could be the photino. The photino is the next vibration up from the standard model. And perhaps that's what we're finding in the laboratory at Fermi Laboratory. So this is creating a lot of excitement.
Now, what part of string theory would suggest that time travel, for instance, is possible? Because you mentioned that later on in the book, and you also mentioned wormholes, through black holes. And I'm just curious, obviously, these things have existed for over 100 years in science fiction, but what in the math suggests they actually might be real?
Well, in 1935, Einstein took two black holes and stuck them together to create a funnel. So you would fall into one black hole and get blasted out the other end. So there would be a black hole on one side and a white hole on the other side. You fall into the black hole, but you're blown out the other end as a white hole. This is called a wormhole, a gateway to another parallel universe. So you can use that to go perhaps faster than the speed of light to build a starship, or perhaps you can go to the past and build a time machine. Now, what's the catch? Einstein himself was the one who came up with these theories, but he doubted that they could actually exist. They may not be stable. Maybe the gateway will close up on you. Maybe it'll explode. For that, you need a quantum theory. Quantum theories can calculate whether they're stable or not, whether they close, whether they stay open, whether they blow up. On Star Trek, they have wormholes all the time, but they worry about how stable they are. And that's what we physicists worry about. That's where string theory comes in. String theory is a quantum theory. It allows you to calculate quantum corrections to a time machine or a wormhole machine to determine whether or not they're stable. You see, that's the missing ingredient. So we can talk wormholes till we're blue in the face. The bottom line is, are they stable? And that's why you need a theory of everything.
And are they stable?
Well, we don't know. The math is this very complicated mathematical problem, so we don't know for sure. Hawking thought that wormholes to a distant point in space is probably possible. He was doubtful about going back to the past, but he thought that yes, it's probably stable to have wormholes that go into another galaxy, for example, faster than the speed of light.
Why did Einstein think that this was possible? Like, what indicates that there might be a funnel? Is it because the black hole's gravity could potentially propel something faster than the speed of light?
Well, see, Einstein did not like the fact that an electron is a point particle, and you get all sorts of infinities if you have a point particle. What is the electric field at the instant that you touch an electron? The electric field is infinite there. So he didn't like that. So he wanted to smooth it out. So he was playing with black holes and married two of them. And he said, well, maybe that's a model for a subatomic particle. But of course, this could also be used to model space-time, in which case you can combine two universes and stick two universes together to get a black hole and a white hole. So there are two possibilities. One is, of course, to model a point particle, and the other one is to create a gateway to another universe.
Now, you mentioned that we understand 3 out of the 4 forces, but we don't understand gravity, and we've never identified a particle for that, the graviton. And you also mentioned in the book that uh, gravity is basically a result of the universe's curvature, that essentially that's what forces us all together. We're held by this curvature somehow. I don't quite understand it, but uh, could it be the case that there's no gravity, but that it's just, a result of how the universe is constructed?
Well, remember, Einstein introduced the picture of a smooth surface. And when we walk on the smooth surface, we have the illusion that we're being attracted by gravity, when actually we're being pushed by the curvature of space. Quantum theory says that there are tiny ripples on this smooth surface, and these ripples in turn act like particles. So that's how the graviton comes about. The graviton is a particle of gravity. And how is it possible that you can get a particle of a smooth surface? It's a ripple, a tiny ripple on a smooth surface. For example, what is the photon? The photon is a particle of light. The graviton is a particle of gravity. Now, Einstein himself probably wouldn't like that. He wanted to keep gravity smooth, period, no more ripples. But that's what the quantum theory does. The quantum theory puts ripples on this curved surface, and these ripples are gravitons, which in turn can be described as musical notes on a vibrating string.
This will be the last super scientific question, because I have another set of questions for you. What's the relation between quantum theory, string theory, and so on, and statistics and probabilities? Because like the famous Schrodinger's cat is roughly like a probability problem.
Well, the fundamental essence of quantum theory versus Newtonian physics is uncertainty and probability. Newton's theory gives you an exact trajectory, an exact number for what a particle does. Does a particle go to the left or does a particle go to the right? Depends on the forces. So Newton's laws gives you an absolute understanding of the motion of an electron. However, quantum theory throws that out the window and only gives you probabilities. A probability of the electron that goes to the right and the probability that the electron goes to the left. Now, Einstein hated that because, well, he believed in the Newtonian idea that things are, either it is or it isn't. It's not halfway between. And it means that you can be two places at the same time. It means that you can disappear and reappear someplace else. And Einstein thought that's horrible. For example, philosophers say when a tree falls in the forest and there's nobody there, did it really fall in the forest if there's no one there to hear it? Well, in quantum mechanics, it's even worse. If there's no one to see a cat, then the cat could be dead, alive, sick, run away, jumping for joy. The cat could be in any state whatsoever. Now, Einstein, this is crazy. But hey, he was wrong. This is the way the universe is. You don't really know where the electron is. In fact, the electron could be two places at the same time. What is that called? It's called the laser. Why is a laser so magical? When people first see a laser, they say, what? Light doesn't behave this way. How come a laser acts like that? It's because the electrons, which make up the laser, can be two places at the same time.
And then what? Like, how does that translate into a laser?
Then you can calculate the energy shells of the electron as they whiz around the atom. In other words, how does a laser work? You pump energy in from the outside, the electrons go to a higher level, and then the electrons decay to a lower level, releasing a photon, and the photons congregate to give you the laser beam. So that's how it works. This whole process of being pumped up and then dropping to a low level is quantum mechanical. And that's why you need quantum mechanics to make a laser work. Newton would be horrified by a laser. Newton would say, wait a minute, that violates everything about Newton's equations. Einstein wouldn't like it either.
Oh my gosh, I love these clothes. Mizzen and Main. That's Mizzen and Main. It really is the most comfortable work clothes. Travel clothes. I had to travel this whole week. I'm traveling for a week and a half, and I just took Mizzen and Main clothes with me. Close out 2023 in style with comfortable, breathable, packable, and machine washable pieces from Mizzen and Main. As you wrap up your year-end goals, enjoy a Mizzen and Main dress shirt that you can wear confidently. I like that they've very just nice, solid colors. I don't really like to get all fancy in patterns and everything, although they do have some pattern shirts, but very comfortable clothes, stretchable pants. It's just super comfortable, but they look professional and you can wear them casually or professionally. I like some of their flannel shirts or untuck shirts. I love untuck. I never tuck in. So again, whether you're shopping for a special someone or giving yourself the gift you really want, I just buy myself gifts. Mizzen and Main is the perfect gift for any guy who works, travels, and or cares about looking and feeling great. As you could tell by my many photos across the internet, I care about looking fantastic. I'm practically a model. And let's be honest, every guy loves to look great. So again, shop now at mizzenandmain.com and save 20% when you spend $130 or more using promo code James. That's promo code James at Mizzen and Main, Mizzen and Main.com. You know what I love about fantasy sports is that even though I'm not going to be a great basketball player or a baseball player or a football player or whatever, I feel like I get to participate and make decisions and use my knowledge of these different leagues or these different sports to compete. So it's like I can pick my team or I can pick my favorite players and I could use my knowledge to make predictions and maybe even make money. So with the basketball season here, you can now pick combo projections across football and basketball from the Specials League on Prize Picks. This is a league created specifically for combo projections that include two or more players from different sports or leagues. Want to play alongside some of Prize Picks' favorite players like rapper Meek Mill and comedian Andrew Schultz, who's also been a guest on this podcast, and I've been a guest on his? You can now find community plays under the promos tab of the app to view entries for some of the biggest names in the Prize Picks community each week. Look, Prize Picks even offers a reboot policy so that your entries stay in play even if one of your players gets injured. For football and basketball games, if you have a player who exits the game in the first half and does not return in the second, that player is rebooted. Prize Picks is the only daily fantasy sports platform with an injury insurance policy. What? So, I love playing it. I love anywhere where I can use analytical ability with my interests to demonstrate some skill and maybe make some money. And I like the game-like aspect. I do wish they had chess as a category on prizepicks.com, but I'll settle for what they've got. Maybe I should make my own fantasy chess league. But in any case, I love Prize Picks. Go to prizepicks.com/James. Use code James for a first deposit match up to $100. That's the easiest $100 you're ever going to make. So that's prizepicks.com/James and use code James. Daily fantasy sports made easy. The future of learning is definitely online. Like, it's such BS that you have to spend $200,000 or take $200,000 in loans and go to some fancy school when it's useless. It doesn't guarantee you a job. Most employers, including me, do not care about degrees or grades or anything like that. We want to care that you love what you're doing, that you know what you're doing, in some cases that you have experience or that you're willing to learn. But people in general love learning and are curious. Like, the key to success is curiosity. And I think masterclass.com is the perfect model for online learning. I'm really happy they're sponsoring this episode. If you're going to give a gift, give the gift of learning. Masterclass makes a meaningful gift this season for you and anyone on your list, because both of you can learn from the best to become your best, from leadership to effective communication to cooking. Let me tell you some of the classes I've taken. I've taken comedy from Steve Martin. I mean, can you believe I can take a class from Steve Martin on comedy, or Judd Apatow, my favorite comedy director? I could take an actual class from him on writing. Wolfgang Puck on cooking. Dan Brown on writing, or Judy Bloom, who's been on this podcast, on writing. By the way, Wolfgang Puck also has been on this podcast. It's such a pleasure. I try to take classes all the time from masterclass.com.
And whether you're watching Masterclass on TV or listening in audio mode in the app or on their site, the quality speaks for itself. It's like these Masterclass instructors are your own personal mentors that are going to help you reach the next level. How much would it cost to take one-on-one classes on comedy from Steve Martin or on chess from Gary Kasparov? You just wouldn't be able to do it. But it would cost hundreds of thousands of dollars. With a Masterclass annual membership, it's $10 a month. Memberships start at $120 a year for unlimited access to one-on-one classes with all 180 plus Masterclass instructors. So it's not just $120 for one instructor. You get all 180 plus Masterclass instructors. Boost your confidence and find practical takeaways you can apply to your life and at work. And if you own a business or are a team leader, use Masterclass to empower and create future-ready employees and leaders. That's the real education in today's world. So this holiday season, you can give one annual membership and get one free at masterclass.com/JAS. JAS, of course, stands for the James Altucher Show. So right now you can get 2 memberships for the price of one at masterclass.com/JAS. Masterclass.com/JAS. Offer terms apply.
Every time I see you talk about this, you always seem so happy and so enthusiastic. And it's really like you've been working on physics since you were 8 years old. And everyone always says, follow your passions. It seems like you're a living example of someone who's followed his passion and actually been made happy by it.
Well,
Would you say that's true?
when I was in elementary school, there was a pamphlet, and the title of the pamphlet was, "So You Want to Become a Physicist?" And it started off by saying, what's the relationship between a baseball player and a physicist? And I said, gee, I don't know. What's the relationship between a baseball player and a physicist? And the answer was, they both get paid to do what they love. And I said to myself, hey, that's pretty good. You mean I get paid to do what I would normally do anyway for free? Yeah. And so I said to myself, that's for me. I want to become a physicist because you can actually get paid to work out the secrets of Mother Nature. See, I like to think of the universe as a chess game. And when you look at a chess game and you don't know the rules, it takes time to figure out how the pawns move, how the bishops move. It takes time to figure that out. I think that's the universe, that we are watching this chess game and that we're slowly figuring out how the king moves and how the queen moves. But that doesn't make us a grand master. That doesn't make us a wizard at chess. No, we're just beginning to find the rules of the game. And that's why I think Mother Nature is so intriguing, that the rules are hidden. But when I discover a new equation, I'd like to think that on the other side of the Milky Way galaxy, there's an alien who is finding the same equation in different notation. And that, to me, is a thrill of a lifetime.
And intelligent humans, let's put it that way, have been around maybe 250,000 years. And obviously, the universe is 13.8 billion years old. Some civilizations might be 1 billion years old versus 250,000 years. And that's substantially larger. Like, you think there are universes, and you have another book about this where you call them like type 2, type 3, type civilizations. Do you think there are civilizations out there that are grandmasters of they've learned the rules 1 billion years ago, and now they've studied so much, they really are grandmasters of how the universe works?
Yes. Some of my friends who are physicists, you talk to them about flying saucers and aliens and outer space, their eyes kind of roll up to the heavens, they shake their head, and they say, no, the distances are so far that the aliens cannot possibly reach the Earth. But you see, that assumed that the aliens are just a few hundred years more advanced than us. Sure, in a few hundred years, we're not going to go to the stars in a starship, but in a few thousand years, in a few million years, then new laws of physics begin to open up. Einstein's equations break down at the Planck energy. The Planck energy is the energy of the Big Bang. It's the energy at the center of a black hole. It's the energy of the string. That's where the known laws of physics break down. That's where wormholes might exist, time machines might exist, and that's a quadrillion times more powerful than anything we can muster. Now, If you work out civilizations, a type 3 civilization, which is galactic, a type 3 civilization like in Star Wars that can roam the galactic space lanes, they may have the ability to access the Planck energy. The Planck energy is the energy at which space and time become unstable. If I have a microwave oven and I can heat it all the way up, eventually I get neutrons, protons coming out of the microwave oven. If I heat it up even more to the Planck energy, then space begins to boil. Bubbles begin to form inside your microwave oven. And what are these bubbles? Bubbles in space-time, wormholes, mini universes. Hawking called this the space-time foam. That's the energy of the Planck energy, the energy at which space and time become unstable. And if you're type 3, a civilization that advanced, and you can harness this power, think about that. You become masters of space and time. Things that are impossible to us become possible to them because space and time, are their plaything. They can play with space and time.
So it's interesting because physicists, and I feel like you in particular, having read many of your books and spoken with you, you're like a modern day philosopher. So 200 years ago, 300 years ago, philosophers maybe focused, they're more comparable to modern day psychologists. Like Freud was kind of out of the cloth of, a Schopenhauer or philosophers around that time. But you now have the tools of physics in terms of asking like questions like, why are we here? What is this place that we're in? What should we be doing? Do we have a purpose? Is, your book's called The God Equation. Is there a God? But let's take these type 3 civilizations because in some sense, they're representative of what we're striving to be. Well, how do you think morality or our view of, our reason to be changes as we become more sophisticated in understanding the rules of the universe?
Well, Galileo, I think, said it best talking about religion, science, and philosophy. He said the purpose of science is to determine how the heavens go. The purpose of religion is to determine how to go to heaven. So to be a scientist means you want to understand natural law, how the heavens go. But if you are a religious person, you want to discuss ethics, how to go to heaven, how to be a good person. Now, the problem occurs when people who are scientific pontificate about ethics, or when religious people pontificate about natural law. That's when we get into trouble. But as long as we keep these two separate, they're complementary. They can help each other. And so I think there's no basic contradiction between science and religion.
Right. So it's almost like physics becomes this unified theory of science. And I'm not even thinking just about religion, but just philosophy in general. Like in order to make it to be a type 2 or type 3 civilization, you have to survive. You have to survive as a species. You have to survive individually. And one way, of course, that there's destruction is through science. And another way that there's destruction is just everybody doesn't get along and there's wars and it all goes away. And so for a civilization to survive to type 3, we know what the goals are, which is to have a deeper understanding of these rules of the universe. But I wonder what you have to become as individuals or as a species in order to be the type of species that discovers these rules.
Well, we are a type 0 civilization. We're at the very bottom. We get our energy from dead plants, oil and coal. And we're just 300 years away from the savagery of the past, where we had witchcraft, sorcery, magic. We're just 300 years from that era of barbarism. And we just came from the swamp, a swamp just 300 years ago. But we're making that transition to type 1. By about the year 2100, we'll be a type 1 civilization that is planetary. We'll control the weather. We'll be able to influence volcanoes and earthquakes. We'll control planetary energy, but we'll still have some of the savagery that we had coming out of the swamp. Now, by the time we're type 2, by the time we have the power of a star, as in Star Trek, Star Trek would be a type 2 civilization. Then you become immortal. Nothing known to science can destroy a type 2 civilization. Asteroids can be deflected. Pandemics can be halted. Global warming, they control the weather. They can control global warming. If the sun goes supernova, they simply leave the sun and go someplace else. So a type 2 civilization is immortal. And type 3 would be galactic. They've spread throughout the entire galaxy, sort of like Star Wars. And so by the time you are immortal, I think that your whole vision of peace and tranquility become part and parcel of how you see your own destiny. I mean, why do people have wars? For many reasons, but among them, power and resources, the resources to reproduce. Because if you don't reproduce, your species dies out, right? And to reproduce, you need resources, so that means you have to fight for them. But by the time you're type 2, you have as many resources as you want because you have the power of the sun. You can just grab a piece of the sun and use that to energize your machines. So I would think, though I cannot prove, I would think by that time we're type 2, then all the savagery would be weaned out of our civilization because there's no purpose. There's no purpose to having wars because the purpose of wars is to get resources so that you can reproduce. But a type 2 civilization is for free. And so I see that by the time you're type 2, they would be peaceful and hopefully they will have outgrown the savagery of their past.
And so, what I'm curious of for you, how does working on all these theories and ideas, and your mind is probably constantly thinking about concepts like what was the beginning of the universe, what invisible hands put it together, what was before the beginning of the universe, and you refer to these concepts in the book. How do you think it changes the way you deal with daily life, on an everyday basis?
Well, I think about these things. My parents were Buddhists. And in Buddhism, there's only nirvana, timelessness, no beginning, no end. And they put me in a Sunday school, a Presbyterian Sunday school. So I learned all about Genesis, where God said, "Let there be light." So I've had these two ideas in my head that the universe had a beginning or the universe didn't have a beginning. There's no two ways around it, right? Wrong. Now there is, because you see, our universe had a beginning. Our universe had a Big Bang. Our universe is a bubble that's expanding. That's called the Big Bang Theory. However, string theory says there are other bubbles out there, other bubbles. And there's a bubble bath of universes. And what is these universes floating in? They're floating in nirvana. In other words, 11-dimensional hyperspace. That's the nothingness of nirvana, out of which Big Bangs are happening. So the Big Bang is a quantum event, meaning that it could happen again. There's a probability that they're happening even as we speak. Even as we speak right now, universes are being created someplace far, far away. And so that's how you meld these two ideas together. The multiverse theory allowed you to combine Buddhism with Judeo-Christian thinking about Genesis, because Genesis happens all the time in an ocean of nirvana.
And these other universes, they might have different rules of physics, right?
Or very similar to ours too. People ask the question, is Elvis Presley still alive in a parallel universe? Well, you can't rule it out that yes, maybe he is belting out these hits in another universe, not our universe. In our universe, he died. But in another parallel time stream, perhaps he's still making hit after hit.
And I always wonder, given your knowledge, let's say you were transported back in time 1,000 years. So you're in 1100 AD and you land somewhere in Europe or Asia or wherever. What good would you be to anybody?
Not much, because the forces of history, the so-called means of production are primitive. The means of production were not sufficient to create plenty. In other words, people had to fight. There was barbarism. People had to fight for limited resources. And once in a while, we had glimmers of a civilization that could be peaceful, but they were usually overwhelmed by the barbarism of the neighboring nation. Now, however, because we have science and technology, we have enough resources to begin to think about what a paradise would look like. In other words, the transition from type 0 to type 1. And we are about 100 years away from attaining type 1 status. Just think about it. The internet is a type 1 telephone system, the first telephone system that is planetary that fell into our century. Well, we're still type 0, but the internet is a type 1 civilization, is a type 1 telephone system. And what language will they speak? A planetary language. Already, English and Mandarin Chinese are the two most common languages on the internet. And so we're already beginning to see the birth of a planetary language. And look at sports. We have soccer and the Olympics, the beginning of a type 1 sports. And take a look at music. We're seeing the beginning of a type 1 music with rock and roll, rap. And we're seeing the beginning of a type 1 fashion with Chanel and Gucci. So we're seeing the beginning of a type 1 civilization right before our eyes, which I think is quite thrilling, because a type 1 civilization will have plenty of time to iron out their sectarian, racial, sexist differences between people to create an age of Aquarius.
So what you're kind of saying, and this is looking at it through the lens of Yuval Harari's *Sapiens*, is that we're starting to tell stories that resonate throughout the entire planet, as opposed to stories and narratives that are tribe by tribe or nation by nation. So the internet is not just a national technology; it's one that unifies the world a little bit. Chanel and Gucci are recognized all around the world, as opposed to being my fashion and you have your fashion.
Yeah, so I think that we're beginning to see the beginning of a type 1 culture on the planet Earth, which I think is a good thing. Now, I differ from other scientists when we talk about the moral direction of technology. Most scientists would say that technology is neutral. It's a double-edged sword, could cut against you or cut with you. But I tend to disagree. I think that technology does have a moral direction because the internet spreads information. Information creates empowerment. People feel energized by getting information that was denied to them under a dictatorship, let's say. And that promotes discussion. And discussion promotes democracy. That's why dictatorships fear the internet, because the internet spreads democracy. Now, when I was young, I still remember learning about the phrase dictator for life. If you work for the United States, CIA, or the Soviet Union, they couldn't get rid of you. You were a puppet. You couldn't get rid of these people. Now, of course, people laugh. There are no more dictators for life anymore. People can seize power on their own because the internet gives them that opportunity. So I think that we're headed in the right direction. There are going to be setbacks, of course, but I think we're headed in the right direction because the internet spreads empowerment. Empowerment spreads democracy, and democracy is a very stabilizing force because democracies never war with other democracies. Think of all the wars that you had to memorize since you were a child, hundreds of them. And how many of those battles were between two democracies? Almost none.
Yeah, that's a good question. I guess because democracy itself is a somewhat new concept.
Yeah, it's a somewhat new concept. But the point is that even though it's a new concept, we have very few democracies that war with each other. Some people think that what about the Union forces and the Confederate forces? Well, the Confederacy was not really a democracy, it was a slaveocracy. But we don't have examples of two major democracies warring with each other. You see, in a democracy, to get people to fight a war is very difficult. You have to convince mothers to sacrifice their children. You have to convince farmers to give up their taxes for the war machine. You have to make all these sacrifices for war. And for why? For the glory of the king? Under a kingship, yeah, it's for the glory of the king. But in democracy, there are no kings. So why should people risk their life for the glory of the king? So I think that it's much more difficult to fight a war if you have democracy. And so I think democracy promotes peace. It doesn't eliminate war, but it makes wars much more difficult to fight as a consequence.
You know, earlier you mentioned how string theory is comparable to music. The music and whether it was a metaphor or whether it actually is a form of music is interesting. But you compared string theory to music, and you also described how it's a beautiful equation and it only fits in an inch and a half, maybe. That would be the God equation. Why is beauty necessary to explain the Big Bang, for instance? Why is beauty necessary to in a physics theory? And you mentioned the math equation, which has E pi I 1 0, and that's very beautiful. But there's some criticism of that too. I forgot the book that recently came out that criticizes the need for beauty in physics. Well, why do you think there is that need, and why do you think it is beautiful and simple?
First of all, what is beauty to an artist and what is beauty to a physicist? To an artist, beauty is something that's aesthetically pleasing, that resonates with their sensibilities. But to a physicist, it's more precise. Beauty is symmetry. That's what beauty is. Why is an ice crystal beautiful? Because you can rotate it. The prongs rotate into themselves in a different order, and it remains the same. A kaleidoscope. Why is a kaleidoscope beautiful? Because when you rotate it, it remains the same. The different parts of the kaleidoscope rotate into another part of the kaleidoscope. Why is physics beautiful? Take a look at E equals mc squared. Because M, matter, turns into E, energy. By flipping these two, you've now unified matter with energy. So with symmetry comes unification. Just like you unify all the prongs of a snowflake, you unify all the parts of a kaleidoscope. Einstein's equation E equals mc squared unifies matter with energy. Now, string theory takes the entire universe, the universe of particles, all the notes on a string, and what does it do? It rotates them. It rotates them into a different set of particles in a different order. It's the same theory, but it rotates into itself. That's why we say equations are beautiful, because the equations rotate components into themselves. String theory takes the entire universe and rotates the universe into itself. It takes the largest symmetry known to science, supersymmetry. That's a symmetry of string theory. And it rotates all the notes into themselves. And that's why string theorists say, this is gorgeous. This is beautiful. What is the object being rotated? The universe itself. And this unifies, therefore, the entire universe. In the same way that energy and matter are unified by E equals mc squared, string theory unifies the entire panoply of subatomic particles.
Well, Michio Kaku, the author of The God Equation, the subtitle's The Quest for a Theory of Everything. And you've also written many great books, about everything from the physics of the impossible to the physics of Star Trek. We've talked about that before when William Shatner was on. The future of humanity, parallel worlds, future of the mind, the physics of the future. What drives you to write these books instead of just focusing on the research that could win you the Nobel Prize?
Well, I do the research anyway, because that's what I do for a living. But as a hobby, I like to engage with people. You see, when I was 8 years old, it was so frustrating because I read that Einstein could not finish this grand scheme of his. So I tried to learn it. I tried to learn about the fourth dimension, about hyperspace, about antimatter. I went to the library and I tried to learn what was Einstein trying to do. And it was so frustrating because there was nothing, absolutely nothing to tell me about the fourth dimension, about all the wondrous things that you see, for example, in science fiction. There was nothing there. So I said to myself, when I grow up and I become a research physicist, I want to at least write some books to engage young people like myself who are frustrated that there's nothing there for them. And so when I write a book, the image that I have in my mind is myself as a child, wondering what's out there. I see these buzzwords like wormholes and hyperspace and antimatter and time machines, but what do the scientists say about these things? That's one motivation that keeps me going, because basically I'm writing for myself as a child.
What I love about them that even though one book is called The Physics of the Impossible, what you demonstrate in the books and how your mind thinks and wanders and wonders is that everything is possible, in certain contexts. And it puts my mind on fire reading your books. And thank you once again for writing this book, The God Equation. And thank you for coming on the podcast. I super appreciate it. And all your explanations of my rambling questions.
Well, it's been an honor to be on your show. Thank you.
Thank you.
Luxury is meant to be livable. Discover the new leather collection at Ashley with premium quality leather sofas, recliners, and more, all built to last. No matter how many spills, scuffs, or pet-related mishaps come its way, the leather collection at Ashley is made with the durability you need for the whole family. Shop the new leather collection at Ashley and find chairs starting at $499.99 and sofas at $599.99. Ashley, for the love of home.